Nuclear power plants are among the most efficient and powerful means of generating electricity, providing a significant portion of the world's energy supply. But how do they actually work? Let's take a closer look. At the heart of a nuclear power plant is the reactor core, where the controlled fission chain reactions take place. Inside the core are fuel rods filled with uranium-235 pellets. Before we move further, let's first examine the science behind the fission chain reaction to better understand what's going on inside the reactor core. In the nucleus of each atom of uranium-235 are 92 protons and 143 neutrons. The total number of protons and neutrons in an atom is called its mass number. The mass number of uranium-235 is 235. That explains the number 235 at the end of its name. The nucleus of uranium-235 is highly unstable because it has a higher number of neutrons than protons. When the unstable nucleus of uranium-235 is bombarded with fast-moving neutrons, its nucleus splits into a krypton-92 nucleus and a barium-141 nucleus, releasing 3 more neutrons and a tremendous amount of heat. The 3 neutrons then split 3 more uranium-235 nuclei, each releasing a krypton-92 nucleus and a barium-141 nucleus, 3 more neutrons and more heat, and the chain reaction goes on. This is an uncontrolled fission chain reaction. Uranium is naturally found mixed with other minerals. However, only about 0.7% of it is the isotope uranium-235. Critical for nuclear reactions. To be useful for nuclear power, the proportion of uranium-235 must be increased to 3 to 5%, a process known as enrichment. Initially, the raw uranium is processed into a substance called yellowcake, which is 80% uranium. The yellowcake is first converted into uranium tetrafluoride, or UF4, and then further processed into uranium hexafluoride, or UF6. The uranium hexafluoride gas undergoes repeated centrifugation until it reaches the required concentration of uranium-235. The enriched uranium gas is then solidified into a usable form. The solid uranium is compacted into pellets that serve as fuel for nuclear reactors. These pellets are placed inside hollow tubes to make the fuel rods, which are inserted into the reactor core for nuclear energy production. Going back to the reactor core, the fission chain reaction is initiated when the fuel rods are placed close to each other inside the reactor core. This starts an uncontrolled fission chain reaction. Control rods made of boron are used to control the fission chain reaction. Boron has the property of absorbing neutrons without releasing one. When control rods are lowered into the reactor core, they absorb excess neutrons and slow down the fission reaction. The heat generated by the fission process is absorbed by the water surrounding the fuel rods in the reactor. This water is kept under extremely high pressure, preventing it from boiling. The superheated water is then pumped into steam generators, where it transfers its heat to the water in the tank. Here, the water does boil and turns into steam. After releasing the heat, water from the reactor is pumped back into the reactor, ready to absorb heat from the reactor core. The steam in the steam generator is directed to a turbine, a large set of blades that spin when hit by the fast-moving steam. As the steam strikes the blades, it forces the turbine to spin. This turbine is connected to a generator, which converts the mechanical energy of the spinning turbine into electrical energy. Inside the generator, spinning magnets around coils of wire create a flow of electrons, which is what we call electricity. Electricity is then passed on to the step-up transformer. The transformer increases its voltage and adds it to the power lines. The power lines then transmit electricity to the end users. After passing through the turbine, the steam is still hot, but it needs to be cooled down so the process can start again. In the condenser, cold water cools the steam, turning it back into water, which is then returned to the reactor to be heated again. The cooling water, which absorbs the heat from the condenser, is released into a cooling tower, where it evaporates as harmless water vapor. Safety is the highest priority in a nuclear power plant. The reactor is housed within a thick containment structure, designed to prevent radiation from escaping. This building can withstand extreme conditions, from earthquakes to tsunamis. Operators in the control room constantly monitor the reactor and its systems, ensuring everything is running smoothly. If necessary, the reactor can be shut down in seconds using control rods. Control rods are inserted into the reactor core to absorb neutrons and stop the fission reaction. This is one of the many ways nuclear power plants are designed to ensure safety. From the controlled power of nuclear fission to the generation of electricity, nuclear power plants play a crucial role in modern energy production. With continued advancements in safety and waste management, nuclear energy remains one of the most powerful tools in the fight for a sustainable future. And that's how a nuclear power plant works, turning the immense power of the atom into the electricity that powers our world.